On the night of October 13th to 14th, 2025, something unusual happened. While most Americans slept, a small group of space exploration enthusiasts discovered something unexpected in NASA's Open Data Archive: the first raw images of the mysterious Comet 3I Atlas, captured by a Martian orbiter just 8 hours before the agency's official announcement of a temporary shutdown. These images weren't supposed to become public this quickly, but the automated data upload system kept working even as administrative staff were already packing up, preparing for an indefinite work break. Write in the comments where you're watching this video from and what time it is for you. I'd love to know who else can't sleep thinking about this story. The story began on July 1st, 2025, when the automated system of the Atlas telescope in Chile detected an unusual object. The computer program flagged a strange trajectory, too elongated for a typical solar system comet. 4 days later, analysis confirmed it. This was the third interstellar object ever discovered by humanity. The greenish glow of the coma indicated the presence of diatomic carbon, making it similar to comets from the Oort cloud. But the orbital parameters told a different story. By mid-September, 3I Atlas had passed perihelion and begun its journey back into interstellar space. That's when Mars Reconnaissance Orbiter operators received an unusual task: attempt to capture the comet from a unique angle. The red planet was in the perfect position to observe an object that Earth-based telescopes were already starting to lose sight of due to increasing distance. The high-rise camera, capable of distinguishing details the size of a desk on Mars's surface, was redirected into deep space. The process of receiving data from Martian orbiters follows a strict protocol. First, images are transmitted to Deep Space Network ground stations, massive antennas in California, Spain, and Australia. Then, the data undergoes initial processing, file integrity checks, and automatic cataloging. Only after that does it enter the Open Planetary Data System Archive, where anyone can download it completely free. Typically, from the moment of imaging to publication takes anywhere from several hours to several days, depending on communication channel load and processing complexity. But on October 11th, negotiations began in Washington about temporary funding for federal agencies. By the evening of October 13th, it became clear that no compromise had been reached. NASA, like many other government organizations, was preparing for a partial shutdown. This meant most employees would have to leave their workplaces, except for staff on critically important missions. Martian orbiters fell into a gray zone. Technically, they continued functioning autonomously, but administrative support and official communications were supposed to cease. The automated data upload system knew nothing about political problems on Earth. At 2:27 a.m. Eastern Time on October 14th, a new data package from Mars Reconnaissance Orbiter completed all processing stages and was placed in the public archive. Among standard images of Martian canyons and polar caps were 4 frames marked as External Target Observation. The target was 3I Atlas. David Chen, a San Francisco programmer and space exploration enthusiast, was the first to notice the files. He had written a simple script that checked NASA's archive every hour for new data from Martian missions. Usually, nighttime uploads contained routine geological observations. But this night, the file index showed something unusual. Chen downloaded the images, opened them in specialized software for viewing scientific data, and froze in front of his screen for several seconds. The images showed an elongated glowing point with a characteristic greenish halo. The comet's coma. The tail, though faint at this distance, clearly extended away from the sun. But the most interesting part was the detail. The high-rise camera's resolution allowed them to distinguish irregularities in the coma's structure. possible gas and dust ejections from the nucleus surface. These were the most detailed images of an interstellar comet ever obtained, and they were sitting in open access, available to anyone with internet and the desire to find them. Chen immediately posted a message on a specialized forum where space data processing enthusiasts gather. Within an hour, 12 more people from different countries joined the analysis: the UK, Japan, Brazil, Russia. They used open-source software to enhance contrast, measure brightness, and build a rough model of the comet's activity. By 6 a.m. Eastern Time, the first processed versions of the images were already spreading across social media. That's when NASA's administrative staff discovered the situation. The official press release with these images was planned for October 17th, after the mission's science team conducted a full analysis and prepared supporting materials. But now the data was already public. Moreover, the agency was in partial shutdown mode, meaning there was no way to quickly organize an official response. The press office wasn't working. Most scientific staff were at home without access to work email. The situation sparked a wave of speculation online. Some users began suggesting that the early release was intentional, a way to bypass supposed censorship during the agency shutdown. Others claimed the images showed something unusual that NASA was trying to hide. But technical staff with system access decided to act on principle. Neither of these theories matched reality, but in the information vacuum, they spread quickly. The reality was much more mundane and simultaneously more interesting. Since the early 2000s, NASA has consistently moved toward an open data policy. Virtually all scientific data from space missions is published in open access as quickly as possible, often within 24 hours of receipt. This allows the global scientific community, including universities in developing countries and independent researchers, to work with cutting-edge data. The system is automated precisely to minimize administrative delays. The technical staff maintaining the automated data transmission systems indeed weren't subject to the shutdown. Their work was considered critical for maintaining communication with spacecraft, but they didn't make the decision to publish the 3I Atlas images. That decision was built into the protocols a month earlier when the observation was planned. The system was simply doing its job, not knowing or caring about the political situation on the planet. To understand why the images ended up in public access so quickly, we need to go back to the open data systems architecture that NASA had been building for decades. In the late 90s and early 2000s, the space agency faced criticism for information secrecy. Universities complained that accessing data from planetary missions took months or years. Independent researchers couldn't get materials at all. This slowed scientific progress and created the impression that space exploration was a privilege of select institutions. The turning point came with the Mars Global Surveyor mission, launched in 1996. By the early 2000s, its operators began experimenting with rapid publication of raw images. The results exceeded expectations. Enthusiasts worldwide started processing images, finding interesting geological formations, and even helping plan future observations. Some discoveries made by amateurs in archival data later became subjects of scientific papers. This proved the value of crowdsourcing in space exploration. By the time Mars Reconnaissance Orbiter launched in 2005, the open access policy had already become standard. The spacecraft was built with automatic data transmission to Earth and immediate publication after minimal technical verification in mind. The system worked like this. The orbiter took pictures, saved them in onboard memory, then transmitted them to Deep Space Network ground stations during communication sessions. These sessions happened several times a day, each lasting from 20 minutes to several hours, depending on data volume and antenna positioning. After receiving the data, an automated process began. Computers checked file integrity, converted them to standard formats, added metadata about imaging time, spacecraft position, and camera parameters. Then, the system generated preview versions in common image formats so anyone could view the images without specialized software. The entire process took 3 to 8 hours. After that, the data was automatically placed in the Planetary Data System, a distributed database accessible through a regular web browser. It's important to understand that this data was truly raw. The high-rise camera aboard Mars Reconnaissance Orbiter shot in red, blue, and infrared ranges with separate detectors. A full-color image required manual alignment of these channels, brightness calibration, and removal of artifacts and noise. Professional planetary scientists used specialized software like ISIS from the U.S. Geological Survey or their own Python scripts, but the basic data was available to everyone simultaneously: NASA employees, university students, and independent enthusiasts alike. When Mars Reconnaissance Orbiter was tasked with photographing Comet 3I Atlas, it was a non-standard operation. Usually, the orbiter looks down at Mars's surface from an altitude of about 300 kilometers. To observe the comet, they had to rotate the entire spacecraft, pointing the camera into deep space. The comet was about 28 million kilometers from Mars on October 3, 2025, the moment of closest approach. That's 70 times farther than the distance from the orbiter to the Martian surface. At that distance, even the powerful high-rise camera couldn't distinguish details of the comet's nucleus. But it could capture the structure of the coma, the cloud of gas and dust around the nucleus. This information held scientific value. Observations from Earth showed that 3I Atlas was actively emitting gases, especially carbon dioxide and cyanide, making it similar to solar system comets despite its interstellar origin. But Earth-based telescopes only saw the overall picture. The Martian perspective allowed viewing the comet from a different angle, helping build a three-dimensional model of its activity. Imaging was conducted in several stages between October 2nd and 7th. Mars Reconnaissance Orbiter took series of images during each pass over Mars's dayside, when solar panels could provide sufficient power for camera operation and data transmission. Each image required precise pointing. An error of even a few arc seconds would mean the comet would be outside the frame. The automatic pointing system used a star catalog for orientation, then corrected direction based on the comet's predicted position. By October 11th, 14 usable images had been obtained. Some contained technical problems, artifacts from cosmic rays hitting the detector, or blur from spacecraft microvibrations. But 4 images were excellent quality. These were the ones transmitted to Earth as priority on October 13th. Transmission began at 7:37 p.m. Eastern Time and took about 4 hours through the Deep Space Network station in Goldstone, California. In a normal situation, the mission's science team would have received notification of new data, conducted preliminary analysis, and prepared a press release explaining what the images showed. This is standard procedure for any significant discoveries. But on October 13th, the situation was anything but normal. In Washington, negotiations continued about temporary government funding. By midnight, it became obvious no compromise had been reached. On October 1st, 2025, a partial federal government shutdown began, the first since December 2018. For NASA, this meant immediate cessation of most operations not related to life safety or critical infrastructure. The press office was closed. The agency's social media stopped updating. Most scientists received notifications of temporary furlough and lost access to work email. But automated systems continued functioning. Technical staff supporting communication with spacecraft, including Mars Reconnaissance Orbiter, Perseverance, Curiosity, and others, were classified as mission critical. They continued working, ensuring spacecraft remained healthy and didn't lose contact with Earth. The automated data publication system also kept working. It didn't require human intervention. It was designed precisely to minimize administrative delays. When the comet images passed automatic verification and processing, the system executed its programmed protocol. It placed the files in the public archive. This happened at 2:27 a.m. Eastern Time on October 14th, 7 hours after the government shutdown began. David Chen, who discovered the images first, didn't know this context. He simply saw unusual files in the archive and downloaded them out of curiosity. When it became clear these were images of an interstellar comet, he followed the usual protocol of the space data enthusiast community, shared the discovery with other researchers. None of them thought about the political context or that these images might be part of a planned but delayed press release. By 8 a.m. on October 14th, processed versions of the images were spreading across specialized forums and social media. Some users created frame-by-frame animations showing changes in the comet's coma structure. Others measured brightness in different parts of the coma, trying to estimate gas ejection intensity. An enthusiast from Brazil combined these images with earlier Hubble telescope observations and built a model of the comet nucleus's rotation. All of this was done using open-source software and published with detailed methodology descriptions so others could verify the results. This is when a parallel reality of interpretation started forming. While enthusiast scientists analyzed the coma's structure and measured brightness, in other corners of the internet, those same images were generating completely different stories. Some users noticed the uneven glow of the coma, a region of increased brightness on one side of the nucleus. For planetary scientists, this was an obvious sign of active gas and dust ejection from the sun-facing side of the nucleus. But for those looking for anomalies, this asymmetry became proof of something unusual. Forums dedicated to conspiracy theories and ufology quickly picked up the topic. Claims emerged that NASA deliberately delayed publishing the images because they showed something contradicting the official version about the comet's nature. The early data leak through the automated system was interpreted as an act of civil disobedience by technical staff, who allegedly wanted the truth out before it could be edited. None of these versions had any connection to reality, but in the information vacuum created by NASA's shutdown, they spread unchecked. The real scientific picture was simultaneously more mundane and more fascinating. Images from Mars Reconnaissance Orbiter showed the comet at about 28 million kilometers, too far for detailed study of the nucleus, but close enough to analyze the coma. The greenish glow clearly visible in the images came from fluorescence of diatomic carbon, a molecule of two carbon atoms that absorbs the sun's ultraviolet radiation and re-emits it in the green range. This effect is typical for comets and has been observed in hundreds of solar system objects. But for an interstellar comet, this was an important discovery. Diatomic carbon forms when more complex carbon compounds break down under solar radiation. Its presence indicated that the icy nucleus of 3I Atlas contains organic molecules, possibly similar to those found in Oort cloud comets. This suggested that comet formation processes in other stellar systems might be surprisingly similar to processes in our system. The interstellar traveler turned out not to be so alien after all, more like a distant relative who grew up in a different house. The coma's asymmetry also had a simple explanation. The comet's nucleus rotates, and different areas of its surface have different composition and temperature. When an area with high volatile content ends up in direct sunlight, intense evaporation begins, ice sublimation. Gas bursts outward, carrying dust particles with it. This ejection creates a bright jet visible as a local enhancement in the coma's glow. Similar jets have been observed in dozens of comets, including the famous 67P Churyumov-Gerasimenko, which was studied in detail by the European probe Rosetta from 2014 to 2016. While debates raged online, the scientific community followed its protocols. The European Space Agency, unaffected by the American government shutdown, continued observations with its Martian orbiters. The Trace Gas Orbiter from the ExoMars mission used the CASIS imaging system, a camera designed to study the Martian surface with a resolution of about 4.5 meters per pixel. For photographing a comet at nearly 30 million kilometers, this was like trying to photograph a mobile phone on the moon from Earth. But the comet's brightness made the task feasible. From October 1st to 7th, Trace Gas Orbiter and Mars Express took several dozen images of the comet at different moments of its approach to Mars. October 3rd saw the closest approach. The comet passed about 29 million kilometers from the red planet. This was a unique opportunity. From Earth, the comet was already starting to get lost in the rays of the setting sun. Its orbit was taking it to the daytime side of the sky, where observations are practically impossible. The Martian perspective was invaluable, the only chance to continuously monitor the object during the critical period of its activity. Nick Thomas, principal investigator for the CASIS camera, later admitted this was one of the most challenging observations for the instrument. The comet was roughly 10 to 100,000 times fainter than typical targets, Martian craters and canyons. Maximum exposure was required, which increased the risk of blur from spacecraft motion, but the result was worth the effort. The obtained images showed a bright point, the nucleus and inner coma, indistinguishable at that distance. Around it spread a dimmer cloud of gas and dust, gradually dissolving into cosmic darkness. Measuring the coma's full size wasn't possible precisely because of this dissolving effect. Dust brightness rapidly decreases with distance from the nucleus, and the coma's outer regions get lost in image noise, random brightness fluctuations created by camera electronics and cosmic rays. But even the visible part extended for tens of thousands of kilometers, evidence of intense nucleus activity. For comparison, the comet's nucleus was estimated to have a diameter of about 5 to 11 kilometers, depending on measurement method and assumptions about its reflectivity. The comet's tail in the October images was barely visible. This wasn't surprising. Tails are much fainter than the coma and only become noticeable on long exposures or during moments of particularly high activity. But astronomers knew that as 3I Atlas approached perihelion, the closest point to the Sun in its orbit, activity would increase. Perihelion was scheduled for late October, when the comet would be about 210 million kilometers from the Sun, roughly the same distance Mars's orbit has from our star. At this time, another spacecraft was preparing for observations, the European probe JUICE, heading to Jupiter. Launched in April 2023, it was on a long trajectory to the gas giant system, using gravity assists to gain speed. In October 2025, the probe was significantly farther from the comet than the Martian orbiters, but its scientific instruments were more powerful and diverse. The plan called for observations to begin on November 2nd, just 3 days after the comet passed perihelion, when it should reach maximum activity. Olivier Huitas, an ESA project scientist working with JUICE, explained the observation strategy. The probe will use 5 different instruments: visible light cameras, an infrared imager to detect thermal emissions, an ultraviolet spectrometer to analyze gas composition, and others. Observations will run from November 2nd to 25th, covering the period when the comet will be most active, but already starting to move away from the Sun. This will allow tracking the dynamics of its behavior, how quickly ejection intensity changes, which gases dominate at different stages, how stable the nucleus rotation is. However, there was one problem. The data wouldn't be available quickly. JUICE's position relative to Earth in November 2025 meant very low data transmission speeds. The enormous distance and non-optimal communication geometry limited channel bandwidth to a few kilobits per second. Under such conditions, transmitting gigabytes of scientific data would take months. Witasi warned that data was only expected in February 2026. Patience would become a necessary quality for everyone waiting for these observation results. While future observations were being prepared, enthusiasts continued working with already available data. The community of space image processors, people who use Open NASA and ESA data to create enhanced versions of images, applied advanced processing techniques. They combined images taken at different times to see changes in the coma's structure, used contrast enhancement algorithms to reveal faint details in the outer regions, built color composites from observations in different spectral ranges to visualize the distribution of various components. Some enthusiasts turned to archival data from other missions. It turned out that the Space Telescope, TESS, Transiting Exoplanet Survey satellite designed to search for exoplanets, had accidentally captured the sky region with Comet 3I Atlas even before its official discovery. Analysis of archival images showed that faint signs of the coma were visible as early as late June 2025, several days before detection by the Atlas telescope. This helped pinpoint when the comet's activity began and build a more accurate model of its behavior as it approached the Sun. When NASA partially resumed operations on October 17th after the short-term shutdown, the press office's first task wasn't debunking rumors, but publishing what should have come out a week earlier, a full scientific analysis of the Comet 3I Atlas images. The document ran 23 pages and contained detailed descriptions of observation methodology, technical imaging parameters, and preliminary findings. There was nothing sensational in it, but there was careful scientific work explaining every detail of the images that enthusiasts had been studying for nearly a week. Astrophysicist Alan Fitzsimmons from Queen's University Belfast, one of the leading experts on interstellar objects, commented on the situation with characteristic scientific restraint. He noted that the premature data publication through the automated system was a technical accident, not a conspiracy. Moreover, such cases had happened before. They just usually involved routine images of Martian dunes that few people cared about. This time, the observation target turned out exotic enough to attract attention, but not mysterious enough to justify conspiracy theories. The comet itself continued its journey, indifferent to earthly debates about its images. On October 29, 2025, it reached perihelion, the closest point to the Sun. The distance was about 203 million kilometers, roughly 1.3 astronomical units. This is closer than Mars's orbit, but significantly farther than Earth's orbit. At this moment, the comet should have reached maximum brightness, around 11th magnitude according to preliminary calculations. But observing it was practically impossible. The geometry turned out extremely unfavorable for Earth-based observers. The comet was almost exactly on the Earth-Sun line, meaning it was lost in the sun's rays. Trying to see it would be like looking for a candle next to a spotlight. Professional observatories weren't willing to risk pointing expensive instruments so close to the sun. Space telescopes like Hubble had protective restrictions, preventing them from pointing at objects closer than a certain angular distance from our star. The most interesting moment in the comet's life passed virtually without witnesses, but the absence of direct observations didn't mean a complete information vacuum. On November 2nd, planned observations began by the JUICE probe heading to Jupiter. Though the distance to the comet was considerable, the probe's instrument suite allowed collecting unique data. The ultraviolet spectrometer registered emission lines from various gases in the coma: cyanide, hydroxyl radicals, possibly atomic oxygen. The infrared imager searched for thermal signatures from dust, heated by solar radiation. Visible light cameras captured the overall morphology of the coma and tail, their day-to-day changes. Olivier Witas had warned about the long wait for results, and his words proved prophetic. The enormous distance between JUICE and Earth in November 2025 limited data transmission speed to levels that would seem slow, even for 90s modems. Priority went to telemetry, information about the probe's condition, which was critical for its safety. Scientific data waited in queue for its turn. February 2026 became the official date when the community could expect first results. However, not all observations required spacecraft. In late November, when the comet began moving away from the sun and appearing in the pre-dawn sky, ground-based telescopes got a new opportunity. The comet moved into the constellation Virgo, low above the eastern horizon before sunrise. Brightness was estimated around 12th to 13th magnitude, too faint for the naked eye, but accessible to medium amateur telescopes with apertures from 20 centimeters. Enthusiasts worldwide began the hunt, traveling to dark sites away from city light pollution. Photographs appearing on astronomy forums showed a pale greenish point with a barely distinguishable fuzzy halo. The tail wasn't visible in most images. Long exposures and careful processing were required to reveal its faint glow. But the very fact of observation mattered. Each image added a data point to the comet's light curve, a graph of its brightness change over time. This information helped understand how actively the nucleus was emitting gas and dust, how quickly the comet was losing mass, whether its behavior matched models built for solar system comets. By December, the comet had moved into the constellation Leo, continuing to move away from both the Sun and Earth simultaneously. On December 19th came the moment of closest approach to our planet. About 270 million kilometers, 1.8 astronomical units. For comparison, this is roughly 700 times farther than the distance to the Moon. At that distance, even large amateur telescopes struggled to distinguish the comet. Its brightness had dropped to 14th magnitude and kept falling. The observation window was closing, but the object's scientific value wasn't limited to direct observations. Analysis of already collected data continued for months after the comet itself became inaccessible to telescopes. Spectroscopic observations conducted in August 2025 by telescopes at MDM Observatory on Kitt Peak in Arizona revealed an intriguing feature. The comet's spectrum showed weak cyanide emission, but lacked lines from more complex carbon molecules typically observed in solar system comets. This phenomenon was called carbon chain depletion. What did this mean in practice? Cyanide is a relatively simple molecule consisting of a carbon atom and a nitrogen atom. More complex molecules like C3 or C2H2 are chains of several carbon atoms. Their absence or low concentration indicated that the chemical composition of material in 3I Atlas's nucleus differed from typical Oort cloud comets. Perhaps formation conditions in the home stellar system were different protoplanetary disk temperature, different element ratios, different history of thermal processing during planetary system formation. This observation echoed data about the second interstellar comet, 2I Borisov, discovered in 2019. It also showed an unusual chemical profile, though different from 3I Atlas. A picture of diversity was emerging. Interstellar comets weren't copies of solar ones, but each had its own individuality reflecting conditions in the stellar system where it was born billions of years ago. 2 comets, too few for statistics, but enough to understand. Each such object is a unique window into the chemistry of another world. Parallel to professional research, enthusiasts continued working with archival data. It was discovered that the TESS space telescope, designed to search for exoplanets by the transit method, had accidentally captured the sky region with the comet back in late June 2025, several days before official discovery by the Atlas telescope. Analysis of these archival images showed weak but distinguishable signs of a coma. This meant the comet's activity began earlier than initially assumed, possibly at a distance of more than 3.5 astronomical units from the Sun. For understanding comet physics, this was important information. The distance where activity begins depends on the composition of ice in the nucleus. Water ice begins intense sublimation only at distances less than 3 astronomical units from the Sun. But more volatile substances, carbon dioxide, carbon monoxide, methane, can evaporate significantly farther out. Early activity of 3I Atlas indicated the presence of such super volatile components, making it similar to some comets from distant regions of the Oort cloud. By the end of December 2025, public interest in the comet began fading. It became too faint for amateur observations, disappeared from news headlines, stopped being a topic of social media discussions. But for planetary scientists, the work was just beginning. Months of analyzing collected data, building models, and writing scientific papers lay ahead. Every detail, the shape of the light curve, gas distribution in the coma, morphology of possible ejection jets, required careful study and interpretation. The story of the premature publication of Martian orbiter images became a footnote in this scientific saga. After a few weeks, it was only remembered as an illustration of how open data systems work and why transparency matters more than control. Conspiracy theories dissolved, finding no confirmation as soon as full data and explanations became available. It turned out the real story, automated systems continuing to work despite administrative problems, was no less interesting than made-up conspiracy scenarios. While discussions about technical aspects of data publication continued, the comet itself delivered scientific surprises one after another. In mid-October 2025, the Neil Gehrels Swift Space Observatory, originally designed to study gamma-ray bursts, pointed its ultraviolet detectors at 3I Atlas. The results were unexpected. The spectrometer detected a bright emission line at a wavelength of 308 nanometers, the characteristic signature of hydroxyl radical, a chemical indicator of water's presence. Hydroxyl in comets wasn't news by itself. Virtually every solar system comet releases water when heated by sunlight, and this water quickly breaks down under ultraviolet radiation, forming hydroxyl radicals. But the emission intensity from 3I Atlas was stunning. Dennis Bodowitz, physics professor at Auburn University and observation lead, calculated the water loss rate, about 40 kilograms per second. He compared this to a fire hose running at full power, continuously pouring water into the cosmic vacuum. Even more surprising was the distance at which this activity was occurring. At the time of observations, the comet was almost 3 times farther from the Sun than Earth, beyond the region where water ice typically evaporates intensely. At that distance, the nucleus surface temperature should have been around -150 degrees Celsius, too cold for water ice sublimation. But the comet ignored these limitations, continuing to lose water at an astonishing rate. This indicated the presence of more volatile substances, possibly carbon dioxide or carbon monoxide, frozen together with water. When such volatile substances evaporate, they can carry water ice particles with them, creating a kind of geyser effect. Something similar was observed on Halley's Comet during its perihelion passage in 1986. Soviet Vega probes and European Giotto detected powerful gas jets ejecting dust and ice from the nucleus's shadow side, where solar radiation was weak. The mechanism turned out to be related to frozen carbon dioxide evaporating beneath the surface, creating pressure and bursting outward, carrying other materials with it. But for an interstellar comet, this observation had deeper meaning. Detecting water proved that chemical components necessary for the emergence of life as we know it aren't a unique feature of our solar system. Somewhere out there, around another star, billions of years ago, a planetary system was forming with conditions similar enough to ours to create icy bodies containing water. This comet was a messenger, a chemical time capsule that delivered material samples from another world directly to our telescopes. Meanwhile, another research group was working on a completely different puzzle, where exactly 3I Atlas came from. Interstellar space is vast, and a comet moving at about 210,000 kilometers per hour could have traveled for millions of years before reaching the solar system. During that time, the gravity of countless Milky Way stars repeatedly changed its trajectory, making the task of determining the starting point extremely difficult. But not impossible. An international team of astronomers used computer modeling to trace the comet's path backward through time. They accounted for the gravitational influence of all known stars in the vicinity of the suspected route, using data from the Gaia Space Telescope catalog, which measured the position and motion of over 1 billion stars in our galaxy. The simulation covered 4.27 million years, a period when modern mammal species were just beginning to form on Earth, and the human genus didn't yet exist. The results, published on the Archive preprint server in early October, were striking. Calculations pointed to a region in the galactic disk where the oldest and youngest stellar populations meet, the boundary between the Milky Way's inner regions and its outer arms. This is where stars born in the galaxy's early youth about 10 billion years ago mix with young luminaries that emerged just a few 100 million years ago. The model identified 62 stars with which the comet could have closely interacted over the last 4 million years. If these calculations are correct, 3I Atlas may be a relic from an early epoch of our galaxy, an object formed when the Milky Way was significantly younger and more active than now. This made it an invaluable scientific target, a kind of paleontological find, only instead of fossilized bones, frozen volatile substances that preserved the chemistry of a protoplanetary disk billions of years old. Each molecule in its nucleus told a story of conditions that existed in that distant stellar system long before the Sun and Earth appeared. On October 29th, the comet reached perihelion, the closest point to our star. The distance was about 203 million kilometers. This was a critical moment. Maximum heating of the nucleus by solar radiation could lead to dramatic consequences. The history of space exploration knew cases when comets couldn't withstand thermal stress and broke into fragments or completely evaporated. Comet Ison in 2013 disintegrated passing perihelion at just 1.8 million kilometers from the Sun. Comet Shoemaker-Levy 9 in 1994 was torn apart by Jupiter's tidal forces into 21 fragments. Harvard University professor Avi Loeb, known for his unorthodox hypotheses about interstellar objects, suggested that the moment of perihelion would become a decisive test for understanding 3I Atlas's nature. If this was truly an ordinary comet, powerful solar radiation would very likely cause its fragmentation. The icy nucleus, heating unevenly, could crack along lines of weakness. Fractures and faults accumulated over millions of years of interstellar travel. But if the object survived relatively unscathed, it would raise questions about its internal structure and composition. Unfortunately, the geometric positioning made direct observations practically impossible. The comet was too close to the Sun on the celestial sphere. Just a few degrees separated it from the blinding disk of our star. Ground-based telescopes couldn't risk pointing optics so close to a light source capable of instantly burning sensitive detectors. Space observatories had automatic protective restrictions preventing pointing at dangerous angles. The most dramatic moment in the comet's life passed essentially without witnesses, leaving scientists waiting for indirect signs. Only in early November, when the comet began moving away from the sun and appearing in the pre-dawn sky, did observations resume. First images showed the nucleus remained intact. There were no signs of fragmentation. Brightness matched model predictions, indicating normal cometary activity without catastrophic ejections. The greenish coma still surrounded the nucleus, though the intensity of its glow began slowly decreasing as it moved away from the sun. The comet survived the test, proving its structural strength. On November 2nd, promised observations began by the JUICE probe heading to Jupiter. Over 3.5 weeks, 5 scientific instruments collected comet data, spectra in ultraviolet, visible, and infrared ranges, high-resolution images, measurements of various gas ejection intensities. Observations in the first days after perihelion, when activity should reach maximum, were of particular interest. But as Olivier Vuittas warned, data remained aboard the probe, slowly transmitting to Earth through a channel with bandwidth measured in kilobits per second. By mid-November, the comet had moved into the constellation Leo, gradually gaining altitude above the horizon in the pre-dawn sky. Amateur astronomers with telescopes of 25 centimeters aperture or more could distinguish it as a faint spot of 13th magnitude. Enthusiasts in Russia, Kazakhstan, and European countries traveled to dark observation sites away from cities, made long exposures, trying to capture the tail that, according to theoretical calculations, should extend several degrees but remain too faint for direct observation. On December 19th came the event amateur astronomers had been waiting months for, the comet's closest approach to Earth. The distance was about 270 million kilometers, 1.8 astronomical units. For comparison, this is 700 times farther than the distance to the moon, but still closer than the comet would ever come to our planet again. After this moment, it began steadily receding, brightness falling, the observation window closing day by day. By the end of December 2025, 3I Atlas had dropped to 15th magnitude at the limit of most amateur instruments' capabilities. Professional observatories continued tracking, but the object now required large telescopes with apertures of a meter or more. The comet crossed Earth's orbit, heading to the outer solar system regions, where its last planned encounter awaited, passing by Jupiter in March 2026. This approach to the gas giant will occur at a relatively safe distance, several tens of millions of kilometers, far enough that the planet's gravity won't tear the comet apart, but close enough for interesting gravitational effects. Jupiter, whose mass exceeds Earth's by 318 times, will slightly alter the comet's trajectory, accelerating or decelerating it slightly, depending on the exact geometry of approach. This last gravitational farewell to the solar system before the final departure into interstellar space. After March 2026, 3I Atlas will pass beyond Saturn's orbit, continuing to accelerate along its hyperbolic trajectory. Brightness will drop so much that even the largest Earth-based telescopes will lose sight of it. The comet will return to the darkness from which it came, carrying with it secrets of its distant home. But it will leave behind terabytes of scientific data, hundreds of images, thousands of spectra, enough material for years of research ahead. Every detail of this data will help bring us closer to understanding how planetary systems form around other stars, how universal the processes are that gave birth to our own cosmic home. By January 2026, 3I Atlas had already become a past tense object for the general public. Brightness had dropped to 16th magnitude, at the limit of even mid-sized professional telescopes' capabilities. The comet crossed Mars's orbit, heading to the outer solar system regions. But for the scientific community, the work was only gaining momentum. Petabytes of data collected over months of observations required careful analysis. Each spectrum, each image, each measurement of gas ejection intensity contained a piece of the puzzle. In February 2026, as Olivier Vitasse promised, data from the JUICE probe began arriving. Terabytes of information collected by 5 instruments over 3.5 weeks in November slowly transmitted across the cosmic gulf. First results exceeded expectations. The ultraviolet spectrometer detected dozens of emission lines, signatures of various molecules and atoms in the comet's coma: hydroxyl, cyanide, atomic oxygen, possibly traces of ammonia, an entire library of chemical compounds telling the story of a protoplanetary disk in another stellar system. The infrared imager discovered an unexpected detail: thermal asymmetry in the dust distribution around the nucleus. One side of the coma was significantly warmer than the other, indicating active ejection from a specific area of the nucleus surface. This effect, known as a jet, has been observed in many solar system comets, but for an interstellar object, this was an opportunity to study rotation dynamics and determine which surface areas are richest in volatile substances. Models showed a rotation period of about 15 hours, typical for comets of this size. Visible light cameras captured changes in the coma's morphology day by day. Some images showed concentric shells, rings of increased brightness expanding from the nucleus. This is a classic sign of periodic gas and dust ejections related to nucleus rotation. When an active region ends up in direct sunlight, intense evaporation begins. Then, after several hours, the nucleus rotates, the region goes into shadow, activity decreases, a new rotation, a new ejection. These pulsations create waves in the coma, like ripples on water from a thrown stone. Combining data from all missions, Martian orbiters, JUICE, Hubble and Swift space telescopes, ground-based observatories, created an unprecedented portrait of an interstellar object. For the first time in human history, we observed a comet from another stellar system with such detail and over such an extended period. The discovery of 2I Borisov in 2019 gave less time for preparation. The comet was discovered already approaching perihelion. 3I Atlas provided several months to plan an observation campaign, coordinate efforts of dozens of observatories worldwide. But the scientific value of this event went beyond the comet itself. The story of premature image publication through the automated system during NASA's shutdown became a subject of discussion in the science communication community. Some saw this as confirmation of the correctness of open data policy. Transparency proved the best defense against conspiracy theories. When data is available to everyone simultaneously, it's impossible to claim the agency is hiding something. A system working automatically without human intervention can't, by definition, participate in a conspiracy. Other researchers noted risks of such automation. What if the images contained technically complex information requiring context for proper interpretation? What if the images showed a truly unexpected phenomenon that could be misinterpreted without expert analysis? In the case of 3I Atlas, we were lucky. The images showed exactly what was expected: a comet with a coma and signs of activity. But the next case might not be so straightforward. The balance between publication speed and quality of scientific communication remained a delicate task. For space data enthusiasts who discovered the images first, this event became confirmation of their role in modern science. Citizen scientists, people without formal scientific degrees but with deep knowledge and access to open data, have long ceased being mere observers. They process images, find new objects in archival data, write software for spectrum analysis. Some are co-authors of scientific papers in peer-reviewed journals. David Chen, who discovered the 3-eye atlas images that October night, was exactly such a person, a programmer by day, a planetary scientist in the evenings. His story wasn't unique. Around the world, thousands of people dedicate free time to studying space, using data that 20 years ago would have been unavailable even to university researchers. This democratization of science is one of the quiet triumphs of the digital age. A 9-year-old schoolchild in India can download the same Mars images as a Stanford professor. A retiree in Australia can find a new comet in telescope archival data missed by automated algorithms. Boundaries between professionals and amateurs are becoming increasingly blurred. In March 2026, the last significant event in 3-eye Atlas's journey through the solar system occurred, passing by Jupiter. The distance was several tens of millions of kilometers, far enough for the comet's safety, but close enough for the gas giant's gravity to make final trajectory corrections. Jupiter slightly accelerated the comet, adding several hundred meters per second to its velocity relative to the Sun. This was enough to shorten its travel time to the heliosphere boundary, the solar wind dominance region, by several months. By April, the comet crossed Saturn's orbit, receding into the twilight zone of the outer solar system. Brightness dropped so much that even the largest ground-based telescopes lost it among millions of more distant stars. The last registered observation was made by the 8-meter Subaru telescope in Hawaii, a barely distinguishable point of 18th magnitude, 250 times fainter than the naked eye visibility limit. After that, 3-eye Atlas disappeared from the field of view of human instruments, returning to the cosmic darkness from which it came half a year ago. But its journey continued. Now, in October 2025, the comet is moving away from the Sun at about 58 kilometers per second. In 10 years, it will cross Neptune's orbit. In 25 years, it will reach the heliopause, the boundary between solar wind and interstellar medium, where the Voyager 1 probe found itself in 2012. In hundreds of thousands more years, it will reach our system's Oort cloud before finally departing into interstellar space. Its path, light years long, will take millions of years. Where is it heading in the interstellar abyss? Modeling conducted by an international team of astronomers pointed to a region in the galactic disk where trajectories of old and young stars intersect. 62 stars were identified as possible points of close passages over the last 4.27 million years. But determining the original stellar system precisely is impossible. Too many gravitational perturbations accumulated over millions of years of wandering. The comet may be a relic of a stellar system that existed 7 billion years ago, more than twice as old as our Sun. This realization evoked almost religious awe in many researchers. 3-eye Atlas wasn't just a cosmic object. It was a message, a time capsule carrying matter samples from an era when the solar system didn't yet exist. Each ice molecule in its nucleus formed in a protoplanetary disk around an unknown star, possibly long extinguished or exploded as a supernova. That stellar system gave birth to this comet, gave it initial momentum, perhaps through gravitational disturbance from a passing star or forming giant planet, and the comet set off on an infinite journey through the galaxy. How many stellar systems has it passed in these billions of years? How many times did it pass on the outskirts of alien planetary systems, invisible and unnoticed? Perhaps millions of years ago it flew past some planet inhabited by intelligent life, and beings looking at the night sky saw a faint moving point, not knowing it was a messenger from another time and another place. Now it's our turn to witness its journey, a brief stop lasting several months in the middle of a path measured in geological epochs. The story of 3I Atlas, like the story of premature publication of its images, became part of a broader narrative about how humanity studies space in the 21st century. Science is no longer a monopoly of government agencies and elite universities. Open data, accessible software, international cooperation, enthusiast participation, all this creates a new research paradigm. When an automated system publishes data in the midst of a political crisis, continuing to work according to programmed protocols, this isn't a bug. It's a feature of a system designed for maximum transparency. In the future, such visits by interstellar objects will become more common, at least in terms of their detection. New generations of telescopes, like the Vera Rubin Observatory with its legacy survey of space and time system, which will begin full observations in 2026, will scan the entire sky every few nights. They'll discover dozens of interstellar objects in the coming decade, each with its own unique history, trajectory, chemical composition. Each will be a window into another planetary system, another epoch of galactic history. And each time such an object is discovered, data about it will be published automatically, becoming available to researchers and enthusiasts worldwide almost instantly. The system created by NASA and other space agencies will continue working regardless of political storms, budget crises, or administrative shutdowns, because space science is too important to depend on the whims of earthly politics. Because knowledge about other worlds belongs not to governments or institutions, but to all humanity. On that quiet October evening in 2025, when David Chen discovered the first 3I Atlas images in the open archive, he didn't think about the historical significance of the moment. He simply followed curiosity, the same force that has made people look at the stars for millennia. But in this simple act, download files, open them, share with others, lay the quintessence of modern science. Openness, collaboration, knowledge exchange without borders or barriers. When systems work correctly, they keep working even when people sleep, even when offices are closed, even when politicians can't agree. Somewhere out there, beyond Saturn's orbit, continues its journey a small, icy world born around another star billions of years ago. It carries secrets we've only begun to unravel. It moves into the darkness from which someday other messengers from other worlds will come. And when they come, the systems will be ready to meet them, record them, measure them, and share that data with everyone who wants to glimpse the echoes of distant worlds. In spring 2026, when Comet 3I Atlas had already disappeared from view of even the most powerful telescopes, the first comprehensive studies based on months of observations began appearing in scientific journals. Each paper added new details to the portrait of the interstellar visitor. One research group from Japan and South Korea published an analysis of the comet's brightness changes, building a detailed model of its nucleus rotation. The period was 14 hours and 42 minutes, remarkably stable for an object traveling millions of years through the galaxy. Another team from European and US universities focused on chemical composition. Combining spectroscopic data from all available observatories, they compiled a complete inventory of molecules in the coma. Besides water, carbon dioxide, and cyanide, traces of methane, ammonia, and more complex organic compounds were discovered. The ratio of these substances differed from typical Oort cloud comets, but resembled some Kuiper belt objects, the cold region on the outskirts of our solar system. This indicated the comet's home system had architecture similar to ours. Particular interest was drawn to work by a group led by Professor Dennis Bodowitz, who directed Swift Space Telescope observations. Their analysis of water loss rate, those same 40 kilograms per second, allowed estimating the total mass of volatile substances in the nucleus. Assuming such ejection intensity persisted throughout several months of activity, the comet lost about 10 million tons of material. This constituted 1 to 5% of its original mass, depending on assumed nucleus size. With each such passage near a star, interstellar comets lose part of themselves, gradually depleting. How many such approaches did 3I Atlas survive during its long life? If the comet's age was truly about 7 billion years, as some models suggested, it could have approached dozens of stars in that time. Each encounter took part of its mass, changed its trajectory, added a new chapter to the history written in layers of ice and dust. Perhaps billions of years ago, it was significantly larger, a multi-kilometer icy body, one of countless building blocks of planetary systems. Now, only a small part remained, but it was enough to tell the story. The galactic trajectory modeling published in March 2026 attracted attention not only from scientists, but philosophers. The idea that the comet could have formed 7 billion years ago, long before the solar system's birth, evoked almost mystical awe. This meant the icy nucleus, now racing away from us at nearly 60 kilometers per second, contains material from an era when the Milky Way was a completely different galaxy. Back then, star formation was more intense, supernovae flared more frequently, the central black hole was more active. The comet, a living witness to that epoch. In April 2026, a year had passed since the Vera Rubin Observatory camera accidentally captured 3I Atlas in images taken 10 days before official discovery. This archival data proved critically important for refining the orbit and determining nucleus size. 11.2 kilometers based on brightness estimates and assumed reflectivity. This was one of the largest interstellar comets ever detected, significantly exceeding 2I Borisov, with its nucleus less than a kilometer in diameter. The Vera Rubin Observatory, with its legacy survey of space and time system, was set to begin full regular observations in the second half of 2026. After reaching full capacity, it would scan the entire southern sky every few nights, creating an unprecedented catalog of changing and moving objects. Design specifications anticipated detecting 10 to 100 interstellar objects per year, depending on their actual prevalence in the galaxy, which remained a subject of debate. The era of individual interstellar visitors was ending. The era of statistics was beginning. Each new interstellar object will add data to understanding how widespread planetary systems are in the galaxy, how they form, what chemical processes occur in them. If most such comets turn out to have similar composition to solar system objects, this will point to the universality of planet formation laws. But if wide diversity is discovered, from water comets to carbon-based, from volatile-rich to nearly inert rocky bodies, this will open windows into countless variations of formation conditions in different stellar systems. The story of premature data publication about 3I Atlas through the automated system during NASA's shutdown became a classic case for courses on science communication and data management. Universities used it as an example of how to design systems for maximum transparency and resilience. Automation, initially implemented for efficiency, also proved to be protection from administrative failures. A system that didn't depend on human decisions couldn't be blocked by human problems. Some critics pointed to risks of this approach. What if data requires context that only an expert can provide? What if automatic publication leads to panic from misunderstanding? But the experience with 3I Atlas showed the opposite. When data became available prematurely, the community of enthusiasts and professional scientists could quickly analyze it and provide context. Conspiracy theories arose, but didn't gain traction because real information was as accessible as speculation. Transparency proved the best antidote to disinformation. David Chen, the San Francisco programmer who discovered the images that October night, continued his work with space data. His script, automatically checking NASA archives for new uploads, became a publicly available tool used by hundreds of enthusiasts worldwide. He didn't become famous, didn't receive prizes or awards. He simply continued doing what he loved, searching for interesting objects in the endless stream of data coming from spacecraft. For him, discovering the 3I Atlas images was one of many lucky moments, though a particularly memorable one. In summer 2026, the first popular book about 3I Atlas came out, written by a science journalist who followed the story from discovery. The book was titled Messenger from Darkness: How an Interstellar Comet Opened a Window to Other Worlds, and combined scientific details with human stories. From Chilean astronomers who discovered the object to engineers who programmed Martian orbiters, from enthusiasts processing images at night to theorists building galactic trajectory models. The book became a bestseller, introducing millions to the reality of interstellar travel. That autumn, a small group of engineers and scientists began informal discussions of a mission concept to intercept an interstellar object. The idea was simple in theory, but extremely complex in practice. Create a spacecraft capable of launching quickly upon detecting a new interstellar visitor, catching up to it, and conducting detailed studies from close range. The speeds were daunting. Even 3I Atlas, with its relatively moderate 58 kilometers per second, moved faster than any human-made object. But with advancing solar sail and gravity assist technologies, the task could become feasible by mid-21st century. Imagine a probe approaching an interstellar comet, landing a module on its surface, taking samples of ancient ice, analyzing their composition right there. Each molecule, a window into another stellar system's chemistry. Each isotopic ratio, a key to understanding conditions that existed billions of years ago in a protoplanetary disk around an unknown star. This would be equivalent to traveling to other stars without needing to leave the solar system's vicinity. Interstellar objects come to us themselves, bringing samples from their distant homes. By the end of 2026, 3I Atlas was beyond Uranus's orbit, continuing its steady retreat from the Sun. Velocity relative to our star reached 90 kilometers per second, a new record among observed objects, just as physicist Marshall Eubanks predicted back in summer of the previous year. No telescope could distinguish it anymore among billions of brighter stars, but the trajectory was known with high precision. Astronomers could predict its position decades ahead, though the practical value of this knowledge was minimal. In 200 years, the comet will leave the heliosphere, the bubble of solar wind surrounding our system. In a few more thousand years, it will pass through the Oort cloud, the hypothetical sphere of trillions of comets on the edge of the Sun's gravitational influence. Perhaps its gravity will slightly perturb orbits of some objects there, sending one or two comets toward the inner system millions of years from now. The echo of its visit will resonate in our system's dynamics long after the object itself vanishes into interstellar emptiness. In several million years, 3I Atlas will arrive at another star. Perhaps there will be a planet with intelligent life, and their astronomers will detect a faint comet appearing from nowhere. They'll conduct observations, measure the trajectory, determine interstellar origin. Maybe their instruments will be sensitive enough to detect unusual traces in chemical composition, a signature of passage through the solar system millions of years ago. Or perhaps the comet will look to them as it looked to us, just another interstellar wanderer, one of millions such objects roaming the galaxy. Somewhere in NASA's archives, on planetary data system servers, those very images uploaded by the automated system on October 14, 2025, continue to be stored. Anyone can download them right now. The same files David Chen saw first, the same pixels that captured a moment in an ancient traveler's life. Data is immortal in the digital age. As long as copies exist, as long as servers run, as long as humanity maintains interest in its own history, these images will be available. They became part of scientific heritage, testimony to a moment when we met a visitor from another time and another place. And in this, perhaps, lies the main lesson of the entire story. Not in the comet's chemical composition, not in its trajectory, not in technical details of automated data publication systems, but in the simple fact that knowledge, once made available, remains available. That transparency is stronger than secrecy. That systems built on principles of openness continue working even when people fail. That curiosity, the very force that made David Chen check the archive that October night, is indestructible as long as mysteries await solving. The comet is gone, but it left behind more than petabytes of data and hundreds of scientific papers. It left a memory of how humanity met a messenger from the abyss, with curiosity, not fear, with instruments, not myths, with openness, not secrecy. And when the next interstellar visitor comes, and it will come, we'll meet it the same way, because we learn to look into the darkness and see in it not a threat, but an opportunity to understand something new about the universe, which turns out to be far more generous with wonders than we could have imagined. By autumn 2027, the story of 3I Atlas had become a classic example in textbooks on astronomy and science communication. Universities analyzed not only the scientific data about the comet itself, but the social phenomenon that accompanied its discovery. Particular attention was paid to the episode with automatic publication of Martian orbiter images during NASA's shutdown, the moment when technology proved its independence from human administrative problems. This case demonstrated that properly designed systems can work even under conditions of institutional chaos. Computer science professors used this episode to illustrate the concept of resilient systems, architectures that continue functioning when individual components fail. NASA's automated data publication system was designed precisely this way, without a single point of failure, without need for constant human oversight. When political negotiations in Washington reached deadlock and most employees were sent home, computers continued receiving data from Mars, processing it, cataloging it, and placing it in public access. The system didn't know about the crisis and couldn't care about it. For science communication specialists, this was a lesson about the power of transparency. Conspiracy theories that arose around the premature image publication quickly vanished as soon as full data and explanations became available. It turned out the best defense against disinformation isn't information control, but its maximum accessibility. When everyone sees data simultaneously, it's impossible to claim someone is hiding something. Transparency makes conspiracies technically impossible, because conspiracy requires secrecy, and secrecy is impossible in a system where everything publishes automatically. By the end of 2027, the Vera Rubin Observatory was operating at full capacity, scanning the southern sky every 3 to 4 nights. In 2 years of full observations, the Legacy Survey of Space and Time System discovered 17 new interstellar objects. Some turned out to be asteroids, dark rocky bodies without signs of activity. Others were comets like 3I Atlas, with comas and tails ejecting gases when approaching the sun. Each object added data to understanding the diversity of planetary systems in the galaxy. Statistics were beginning to emerge. Of 17 detected objects, 12 showed signs of cometary activity, indicating the presence of volatile substances, ices capable of evaporating when heated. Chemical analysis conducted for the 6 brightest objects showed an interesting pattern. All contained water, though in different proportions. 3 demonstrated high carbon dioxide content, like 3I Atlas. 1 proved rich in carbon monoxide, an even more volatile substance. Diversity was significant, but water was present everywhere. This pointed to the universality of processes creating icy bodies in planetary systems. An international team of astronomers published a meta-analysis of all interstellar objects discovered from 2017 to 2027, including Oumuamua, 2I Borisov, 3I Atlas, and 14 subsequent discoveries. The work ran 112 pages and contained thousands of graphs, tables, and spectra. The main conclusion was unexpected. Interstellar objects turned out more similar to objects in our solar system than assumed. Differences existed, but they fit within the range of variations observed between Oort cloud and Kuiper belt comets. This meant planet formation laws were indeed universal. But there were also a few outliers, objects that didn't fit the general picture. One of them, designated 7I Centaurus, discovered in August 2027, showed anomalously high reflectivity and almost complete absence of volatile substances. Spectroscopy revealed signs of silicates and possibly metals, composition more typical of inner regions of planetary systems, where temperatures are too high for ice condensation. This raised an intriguing question. How did an object from another stellar system's inner regions get ejected into interstellar space? Catastrophic events were required. Perhaps a close stellar passage or giant planet formation that destabilized inner orbits. In March 2028, NASA announced the start of preliminary studies for an interstellar object intercept mission concept. The project received the codename Messenger. The idea was to create a spacecraft capable of launching quickly upon detecting a suitable target and reaching it for detailed close-range studies. Technical problems were enormous. Even a relatively slow interstellar object moves at tens of kilometers per second. Catching such a target, matching its velocity, and conducting research required revolutionary technologies. Preliminary design assumed using a combination of chemical rockets for Earth atmosphere escape, a gravity assist at Jupiter to gain additional speed, and possibly a solar sail or nuclear engine for final acceleration. Even under the most optimistic calculations, the mission required a minimum 5 years of preparation from the moment of detecting a suitable target to launch. This meant the object had to be detected several astronomical units from the Sun on approach, leaving enough time for mission preparation. The Vera Rubin Observatory was making such early detections increasingly likely. Meanwhile, European and Japanese space agencies were developing their own concepts. The European Space Agency proposed a more ambitious approach, not just a flyby of an interstellar object, but accompanying it for several months with gradual approach. This would allow observing activity changes during perihelion passage, studying gas ejection dynamics, possibly even attempting to sample the coma, the cloud of gas and dust around the nucleus. The Japanese agency was considering a lander concept similar to the one that successfully landed on asteroid Ryugu in 2019. But landing on a rapidly rotating icy nucleus-emitting gas jets was orders of magnitude more complex. By early 2029, data collected about 3I Atlas 5 years earlier was still being analyzed. Researchers from MIT published a detailed study of the comet's rotational dynamics based on analysis of brightness changes and coma morphology in images taken in October-November 2025. It turned out the nucleus didn't just rotate with a period of about 15 hours. It also showed signs of precession, a slow wobble of the rotation axis similar to a slowing top's motion. The precession period was about 72 days. This observation had significance for understanding the nucleus's internal structure. Precession occurs when mass distribution inside an object is non-uniform. Perhaps 3I Atlas's nucleus had regions with different densities, areas of pure ice, and areas with high dust or rock content. Or perhaps cavities existed inside, formed when volatile substances evaporated during previous approaches to other stars millions of years ago. Each such detail added strokes to the portrait of an object wandering the galaxy for an unimaginably long time. Discoveries continued in the archives. A student from the University of Colorado, sorting through TESS Space Telescope data from June 2025, discovered even earlier signs of 3I Atlas activity, a faint brightness increase in images from June 19th, 12 days before official discovery. This pushed back the start of observable activity to a distance of about 3.7 astronomical units from the Sun, farther than previously assumed. The paper about this discovery was published in the journal Icarus, dedicated to planetary science. The student became a co-author, along with 3 professors who recognized her work processing archival data. Stories like this were becoming increasingly frequent. The boundary between professional astronomers and enthusiasts continued to blur. Open data, accessible processing tools, online courses in planetary science, all this created a new generation of researchers, not necessarily having formal scientific degrees, but possessing deep knowledge and the ability to make significant discoveries. Some universities began recognizing such work when admitting students to master's and doctoral programs. Publications in scientific journals and discoveries in archival data were valued equally with formal education. David Chen, that same San Francisco programmer who discovered the first 3I Atlas images in October 2025, by 2029, had become co-author of 7 scientific papers on Martian orbiter data processing. His script for automatically checking NASA archives was used by hundreds of enthusiasts worldwide and was officially included in the list of recommended tools on the Planetary Data System website. He didn't leave his main programming job, but space research became an integral part of his life. Evenings and weekends he analyzed images, looked for anomalies, helped other enthusiasts understand technical details of data formats. His story wasn't unique, but it was telling. In the 21st century, space science ceased being a monopoly of government agencies and elite universities. Anyone with a computer and internet could download the same data studied by professors at Cambridge or Caltech. Anyone could write a program to process it, find an interesting detail, share it with the community. From such small contributions, big science was built, distributed, democratic, open. Somewhere out there, beyond Neptune's orbit, continued its journey a small, icy comet born around another star 7 billion years ago. No telescope could distinguish it anymore among trillions of brighter objects, but data about it continued to live, be analyzed, generate new discoveries. Each year, someone found a new detail in archival images, a new pattern in spectra, a new interpretation of already known facts. Data was immortal as long as copies existed and people interested in studying them. And when in several decades, 3I Atlas leaves the heliosphere and begins its new interstellar journey stretching millions of years, its visit will remain captured in terabytes of data, hundreds of scientific papers, thousands of images. Future generations of astronomers will return to these archives, applying new analysis methods, new theories, new understanding. Each era will reread this story in its own way, finding in it answers to questions we haven't yet learned to ask. Because real science doesn't end with an object leaving view, It begins anew with everyone who opens this data and wonders, what else can we learn? By early 2030, Project Messenger moved from the conceptual study stage to preliminary design phase. The Southwest Research Institute in San Antonio completed detailed flight plan development that would allow a spacecraft to intercept an interstellar object like 3I Atlas. Calculations showed that detecting a target about 5 astronomical units from the Sun would give the team sufficient time for mission preparation. Launch could occur within 18 months, allowing the craft to catch the object for a series of scientific observations during flyby. Technical requirements were formulated taking into account experience studying 3I Atlas and subsequent interstellar objects. The spacecraft should carry a suite of instruments to study the body's physical properties, determine its chemical composition, and analyze the coma and tail. Special attention was paid to creating an imaging system capable of obtaining detailed nucleus images from several thousand kilometers during flyby at relative speeds of tens of kilometers per second. This required revolutionary stabilization and pointing technologies capable of compensating for rapid movement and vibrations. Project funding remained a subject of debate. Preliminary cost estimates ranged from $800 million to $1.5 billion, depending on chosen propulsion system configuration. Using traditional chemical rockets with gravity assists was cheaper, but limited the range of accessible targets. Including a nuclear electric engine or experimental solar sail significantly expanded capabilities, but doubled cost and technical risks. NASA planned to make a final funding decision by 2032. Ground-based capabilities for detecting interstellar objects were developing in parallel. By 2030, the Vera Rubin Observatory had operated 4 full years in legacy survey of space and time mode, creating the most detailed catalog of variable and moving objects in astronomy history. During this period, 37 interstellar objects were discovered, more than all previous years since Oumuamua's discovery in 2017. Statistics were becoming increasingly reliable, allowing estimation of the real density of such objects in interstellar space. It turned out interstellar wanderers were significantly more common than early models assumed. Calculations showed that each year several hundred objects of extrasolar origin pass through the solar system's inner regions, though most are too faint for detection by modern instruments. Beyond Neptune's orbit, their number reached tens of thousands per year. The galaxy turned out to be filled with these wanderers, planetary system debris ejected by gravitational perturbations billions of years ago and drifting between stars ever since. Each new discovery added details to the growing understanding of planetary system diversity. Some interstellar objects were rich in water and volatile substances, like Oort cloud comets. Others turned out to be dry, rocky bodies, more resembling main belt asteroids. Objects with high carbon content were discovered, possibly arriving from systems where carbon compounds dominated over silicates. One particularly exotic object showed spectral signs of water ice mixed with ammonia and methane, composition typical of outer planet moons like Enceladus or Europa. The story of 3I Atlas gradually transitioned from current events to classic cases. University planetary science courses used it as an example of how modern science studies interstellar objects. The case of premature image publication became a classic example in science communication and data management courses. Students analyzed how automated systems can be more resilient than systems depending on human decisions. How transparency serves as better protection from conspiracy theories than information control. David Chen, who became a symbol of citizen science after that October morning in 2025, by 2030 was co-author of 23 scientific papers. Some were devoted to processing Martian orbiter data, Others analyzed archival images from various space missions. His script for automatically checking NASA archives evolved into a full-fledged application with a graphical interface used by thousands of enthusiasts worldwide. He didn't become a professional astronomer, didn't move to work at a university or space agency. He simply continued doing what he loved, searching for interesting things in the endless stream of space data. His story was one of thousands. Around the world, people of different professions, ages, and education levels contributed to space research. A teacher from Kenya discovered a new class of polar vortices on Mars, analyzing archival images. A retiree from Japan compiled the most detailed catalog of dust devils on the red planet, spending 3 years viewing thousands of images. A group of students from India developed a machine learning algorithm for automatically detecting new craters, which NASA incorporated into its operating systems. Boundaries between professionals and amateurs became virtually indistinguishable. Somewhere out there, far beyond Pluto's orbit, continued its silent journey a small icy comet born around an unknown star billions of years ago. No telescope could distinguish it anymore. No detector registered its faint glow among trillions of brighter objects. But it kept moving, carried by momentum received in another epoch of galactic history. Every second it moved away from the sun by 58 kilometers. Every hour by 208,000. Every year, almost 2 billion kilometers. In a few centuries it will reach the heliopause, the boundary between solar wind and interstellar medium. There, where the Voyager 1 probe found itself in 2012, where particles from our star mix with matter between stars. Then the comet will enter the Oort cloud, the hypothetical sphere of trillions of icy bodies on the far edges of the sun's gravitational influence. Perhaps it will pass close enough to some objects there that its gravity will slightly change their orbits. In millions of years, these changes may send 1 or 2 comets toward the inner system. The echo of its visit will resonate in our system's dynamics for a long time, but it will be unnoticeable. Perturbations too small, effects too slow, time scales too enormous for human perception. The comet will simply pass by, as it has passed countless other stellar systems during its long existence. Nothing will mark its presence in that distant darkness, except invisible changes in other icy bodies' trajectories, and in several thousand years it will exit the Oort cloud on the other side, finally leaving the sun's sphere of influence. Its next stop will be in several million years, at another star. Perhaps there will be planets. Perhaps one will be inhabited. Perhaps beings on that planet will detect a faint point of light moving in a strange trajectory relative to background stars. They'll point their instruments at it, measure the spectrum, determine composition. They'll see water, carbon dioxide, organic molecules. They'll understand this isn't part of their system, but a guest from interstellar space. And perhaps they'll feel the same awe we felt looking at images that October night in 2025. Or perhaps no one will see it. Perhaps it will pass through that system unnoticed, as it passed through thousands of others over billions of years. Not every journey has witnesses. Not every story gets told. Most interstellar wanderers drift in darkness forever, never approaching close enough to a star to heat up and begin ejecting gases, never entering a telescope's field of view. Simply existing in the silent void between luminaries, storing in their icy depths the chemistry of long-vanished worlds. But 3I Atlas was one of the lucky ones. Its path intersected the solar system at the moment when civilization on the third planet existed with technology for its detection and study. Not 1,000 years earlier, when people were just beginning to build telescopes and couldn't have distinguished it among millions of stars. Not 1,000 years later, when perhaps humanity would possess even more advanced instruments, but the comet would have already passed by. Precisely in this brief interval of cosmic history, trajectories aligned, and this encounter left a mark. In planetary data system archives, terabytes of data about 3I Atlas continue to be stored. Each image, each spectrum, each brightness measurement is available to anyone with an internet connection. Those very images David Chen discovered that October night, the first images of an interstellar comet from a Martian orbiter, published by an automated system during NASA's shutdown, remain on servers, as accessible today as then. Data doesn't age. It doesn't fade. It simply exists, awaiting the next researcher, the next question, the next discovery. And in this perhaps lies true immortality, not in the physical object receding into darkness, but in information about it, preserved and distributed. The comet left, but its story remained. Every student studying planetary science will learn about 3I Atlas as a classic example of an interstellar object. Every science communication specialist will study the case of premature data publication as an example of resilient systems. Every future mission designer to interstellar objects will use data about it for planning trajectories and selecting instruments. The comet gave us more than scientific data. It reminded us that the universe is full of wanderers, objects that belong to no stellar system but drift between them, carrying stories of their distant homes. That the galaxy isn't a set of isolated systems, but a unified whole, where matter constantly exchanges, where planetary building blocks travel from star to star. That boundaries between ours and alien blur at cosmic scales, because all matter in the universe is a product of the same physical processes governed by the same laws. And it reminded us that knowledge is better than mystery, that transparency is stronger than secrecy, that systems built on openness continue working even when people fail, that curiosity is the most powerful force humanity possesses. Curiosity made someone write a script, checking NASA archives every hour. Curiosity made someone open unusual files that October night. Curiosity turned a simple detection into a global scientific event. Somewhere in the darkness between stars continues its journey a small, icy world. It carries secrets we've only begun to unravel. It moves toward encounters we'll never know about. But for a brief moment of cosmic history, our paths crossed, and that moment was captured, studied, understood, and preserved for future generations, not because some agency decided to do so, but because the system was designed correctly, transparent, automatic, resilient, and because there were people curious enough to look into darkness and see in it not emptiness, but an opportunity to learn something new. When the next interstellar visitor comes, and it will come, we'll meet it the same way, with instruments ready for observation, with systems ready to publish data, with a community ready to analyze, and with the same quiet awe before the wonder. Somewhere out there, around another star, billions of years ago, a planetary system was forming, and a small piece of that distant world reached us, crossing the abyss of space and time to remind us for a moment, we're not alone in this galaxy, not in the sense of intelligent life, but in a deeper sense. The chemistry that gave birth to us is universal. The processes that created our system happen everywhere, and between all these worlds exists a connection, thin, invisible, but real, in the form of these eternal wanderers. Years have passed since that October morning in 2025, when a simple script discovered unusual files in NASA's archive. Years have passed since an automated system, unaware of political problems on the planet below, calmly did its job, received data from a Martian orbiter, processed it, and placed it in public access. But the lesson of that moment remains relevant. Systems built on principles of transparency and automation proved more resilient than the most carefully designed administrative structures. When people failed in negotiations, when offices closed, when email stopped working, computers continued their quiet work. This story became more than just an episode in studying one comet. It turned into a parable about how modern science should work, not through control and secrecy, but through openness and accessibility, not through centralized decisions by a select few, but through distributed participation of thousands of interested people worldwide, not through institutional monopoly, but through democratization of knowledge. When data is available to everyone simultaneously, science stops being a privilege and becomes a right. The right to ask questions, seek answers, participate in the great process of understanding the universe. Comet 3. Atlas long ago disappeared from our telescopes, continuing its silent journey through the void between stars. Every second it moves away from us by tens of kilometers. Every year, by millions. In centuries, it will leave the sun's sphere of influence forever, returning to that infinite darkness from which it came. But information about it remains. Images, spectra, measurements, all this continues to exist in archives, available to anyone who wants to look. Data doesn't know about distances. It doesn't care where the object of its description is located. It simply stores truth, patiently awaiting the next researcher. There's something deeply comforting in this. In a world full of uncertainty and change, where political storms come and go, where institutions experience crises and reforms, where technology changes at dizzying speed, these quiet archives remain. Terabytes of space data collected over decades of observations, available to all without exception. Knowledge that can't be taken away, can't be closed, can't be monopolized. It simply exists, as stars exist in the sky, indifferent to our problems, but always available to those who look up. David Chen, who became an unwitting symbol of citizen science, continued his quiet work, not in search of fame or recognition, but simply because it brought him joy. Every evening, after his main work, he opened his computer and checked archives. Sometimes he found something interesting, an unusual crater on Mars, a strange cloud in the atmosphere, a dust devil trace in a photograph. Sometimes he found nothing. But the search process itself, this feeling of exploring an endless data stream, the ability to touch something greater than daily life, this was reward enough. Space demanded nothing from him in return. It simply allowed him to look, study, marvel. His story repeated thousands of times around the world. Teachers in rural schools showing students real images from Mars. Retirees dedicating free time to classifying galaxies or searching for exoplanets. Students making discoveries in archival data that professional astronomers missed. All of them were part of one invisible community, people united by curiosity and access to knowledge. Boundaries between countries, cultures, social classes lost meaning when it came to images of distant worlds. A Martian crater looked the same to everyone, whether viewed by an Oxford professor or a Nigerian schoolchild. This democratization of science became possible thanks to those same automated systems that kept working during NASA's October shutdown. They were designed without ulterior motives, simply for efficiency, to minimize delays between receiving data and publishing it. But in the process, they created something greater. A system that couldn't be closed by political decisions. A system that by definition knew no secrets. A system that treated everyone equally, from NASA's director to a curious teenager. Everyone received access to data at the same moment. Of course, there were critics. Some argued that premature publication of raw data could lead to misunderstanding, that images without expert context could be misinterpreted, that speed shouldn't prevail over quality of science communication. And there was truth in these arguments, but the experience with 3I Atlas showed the community was capable of providing context itself. When images appeared in the archive that October night, enthusiasts didn't just download them and start inventing theories. They applied the scientific method, measured brightness, compared with previous observations, built models. And when speculation appeared, there were those who patiently explained reality. Transparency proved the most reliable defense against disinformation, not because it prevented false theories from appearing, those always appeared, but because it made truth as accessible as fiction. In the battle between facts and speculation, when both sides have equal access to the audience, facts usually win, especially when facts are backed by data anyone can verify. A conspiracy theory crumbles when raw data is available for everyone to analyze. It's impossible to claim NASA is hiding something when literally every pixel of every image is in public access. Perhaps the most important lesson of the entire story was understanding that great discoveries often happen not in moments of triumph, but in moments of quiet, methodical work. Not when press offices prepare loud announcements, but when automated systems calmly perform their functions. Not when scientists make sensational statements, but when enthusiasts patiently sort through data looking for interesting details. Big science is built from millions of small moments, a script checking an archive every hour, a computer processing images at 3 a.m, a person deciding to spend their day off analyzing spectra of a distant comet. 3I Atlas gave us more than data about another stellar system's chemistry. It reminded us of the universe's connectivity, that matter travels between stars, that planetary system boundaries are permeable, that we're all part of a galactic exchange of matter and information happening on scales of millions and billions of years. Somewhere out there, around another star, billions of years ago, a protoplanetary system formed. Some of its building blocks were ejected into interstellar space. One of them reached us, and for a brief moment, we could study it, understand it, extract from it information about that distant world. And now this object continues its journey, carrying with it not only the chemistry of its native world, but the invisible trace of our observation. Photons from our radars touched its surface. Our telescopes collected light, reflected from its coma. Our instruments analyzed the spectrum of its emissions. These interactions are infinitely small on cosmic scales, a few kilograms of electromagnetic radiation striking a multi-ton icy nucleus. But for us, they meant everything. A chance to glimpse another world, a chance to expand understanding of the universe, a chance to touch something ancient and eternal. Somewhere in archives, on unnamed servers distributed around the world, those very first images continue to be stored. Images uploaded by the automated system at 2:27 a.m. that October morning. They look the same as they did then. The same pixels, the same greenish point against the black background of space, the same metadata about imaging time and camera parameters. Nothing has changed in them over the years. They simply exist, patiently awaiting the next person who will open them and ask, "What can this comet tell me about the universe?" And in this constancy of data lies its own beauty. The world changes. Technology evolves. Theories are revised. People come and go, but facts recorded digitally remain unchanged. These images will show the same thing in 10, 20, 100 years. They'll become historical documents, testimony to the moment when humanity met a visitor from another world. They'll be studied by future generations with the same tools or with completely new ones we can't yet imagine, and each generation will find something of its own in them. Perhaps in decades, someone will develop a new image analysis method capable of extracting from these pixels information we missed. Perhaps future artificial intelligence will discover patterns in the comet's brightness distribution, indicating composition details invisible to modern instruments. Perhaps combining this data with information from an intercept mission that someday reaches another interstellar object will allow understanding processes we can now only guess at. Data is patient. It can wait as long as necessary. And the comet continues its path through the galaxy, invisible, unnoticed, forgotten by all except those few who occasionally return to archival data about it. It moves in darkness between stars, carrying in its icy depths the chemistry of a long-vanished world. In millions of years, it will arrive at another star. Perhaps there will be beings capable of noticing it. Perhaps they'll ask the same questions we asked. Perhaps they too will build systems for automatic data collection and distribution. And perhaps they too will understand that knowledge becomes more valuable when shared, not when hidden. In the quiet darkness of space, there's no politics, no borders, no secrets. There's only matter, energy, and laws of physics, the same everywhere. The comet doesn't know where it's from or where it's going. It simply exists, driven by momentum received billions of years ago. But we, observing it, learn to see connections between stellar systems, between past and future, between knowledge and understanding. We learn to build systems that serve not power, but truth. Not control, but openness. Not a select few, but everyone willing. And when the next interstellar visitor comes, and it will come, automated systems will be ready. They'll receive data, process it, place it in public access, without delays, without censorship, without preferences, simply doing their job as they did that October night in 2025. And somewhere in the world, a person like David Chen will check the archive, discover new files, and share the find with others. And the cycle will repeat: discovery, analysis, understanding, knowledge distribution. A quiet revolution that needs no manifestos because its principles are embedded in automated system code. Transparency, accessibility, universality. Science for all, not for the chosen few. Sleep peacefully, knowing that somewhere out there, in the darkness between stars, messengers from other worlds continue their journey. And when they come to us, we meet them not with fear, but with curiosity. Not with secrecy, but with openness. Systems work, data is preserved, knowledge spreads, and everyone who wants to glimpse echoes of distant worlds can do so, simply by opening a computer and entering the right archive address. The universe awaits those ready to look.